When you drive at 65 miles an hour, the road beneath you feels like a simple, static ribbon of black tar. We rarely think about the pavement until a pothole rattles our teeth. But underneath that smooth surface lies a highly complex, multi-layered engineered system. It is specifically designed to absorb and distribute millions of tons of compressive force every single day. To an engineer, a road is only acceptable if it meets strict operational parameters. It has to maintain an International Roughness Index, or IRI, of under 2.7. It also has to proactively manage kinetic energy, acting as a physical buffer to keep human bodies safe during a crash. That quiet, comfortable ride you experience is not a given. The surface smoothness is just the final visible indicator of a massive hidden structural achievement. If construction teams ignore the unmapped variable ground conditions beneath a site, the roadway will quickly succumb to severe structural shearing and deep rutting. The financial toll of these failures is immediate. On a micro level, routing a heavy delivery truck over a badly deteriorated surface spikes its vehicle maintenance costs by up to 121%. On a macro scale, poor roadway design increases the frequency of collisions, creating enormous economic drag. In 2010 alone, motor vehicle crashes cost the United States $836 billion in direct economic and societal harm. A failing road is a localized financial disaster. Building these corridors perfectly from the ground up is an absolute economic necessity. Roughly 80% of all highway engineering failures originate deep underground. Before paving begins, geotechnical teams map the soil stratigraphy to determine its California bearing ratio, a specific measure of the native dirt's strength. Contractors then clear the site using a cut and fill method. They excavate earth from high points and transport it nearby to build embankments, reducing the need for expensive transport and soil disposal. The newly exposed dirt, or subgrade, forms the foundational base. If highly plastic or moisture sensitive, it compresses under traffic, requiring subgrade stabilization. While conventional methods use lime, modern roads use engineered polymer stabilizers. These coat soil particles, locking them into a water-resistant flexible matrix. This stabilized layer prevents top-down roadway failure by providing an unyielding foundation that refuses to sink. With a solid subgrade in place, crews lay down graded, angular rocks to form the capping, subbase, and base courses. To keep these rocks from shifting laterally under pressure, engineers integrate geosynthetic materials. They roll out high-strength geogrids, an interlocking mesh that tightens around the aggregate, locking site materials in place under heavy weight. Inspectors then perform a proof roll. They drive heavily loaded dump trucks over the compacted stone to identify any hidden, localized deflections. These middle sections act as the road's shock absorbers, protecting the fragile subgrade from the crushing kinetic weight of the vehicles moving above. Finally, the road is ready for its pavement layer. At this stage, highway engineering splits into two philosophies based on how structures handle physical load. The first is flexible pavement, commonly known as hot mix asphalt. This multi-layer design physically yields to traffic weight, transmitting compressive stress downward from individual grain to grain. To combat summer rutting and winter cracking, high-grade flexible roads mix elastomeric polymers into the asphalt. This creates a cross-linked network that significantly increases the road's resistance to extreme thermal fatigue. The alternative is rigid pavement, constructed from hydraulic cement concrete. Instead of yielding, rigid roads operate on plate theory. They use a high modulus of elasticity and continuous steel reinforcement to distribute massive, concentrated loads widely across a stiff, unbending slab. Once the pavement cures, crews apply durable thermoplastic striping for lane markings. Quality assurance teams check surface elevations, verify proper drainage paths, and measure the ride profile. The physical structure is complete. It has been meticulously engineered from the dirt up to carry the literal and metaphorical weight of the country. Zoom out from those freshly painted lane markings to the national grid. At this scale, the highway system functions as a dynamic macroeconomic transmission mechanism. In macroeconomic theory, this operates through the public investment multiplier effect. When a government injects funds into high-quality transportation infrastructure, that initial spending acts as a catalyst, stimulating massive long-term economic output. The first way this generates wealth is through agglomeration economies. High-speed, well-maintained corridors effectively shrink physical distance. They reduce travel times and costs, bringing geographically dispersed businesses, suppliers, and workers closer together. This newly accessible density increases labor market efficiency, speeds up the exchange of ideas, and directly boosts a region's overall productivity. Smooth, reliable roads also allow corporations to completely restructure how they build and sell products. Fast transport links enable just-in-time inventory management, allowing businesses to minimize expensive warehousing costs by receiving materials exactly when they need them. This is a line chart tracking the financial return on public infrastructure investment in the United States. It shows that for every single dollar spent on the public road network, private industries realize an average of 18 to 24 cents in production savings every year. This relationship governs international trade elasticity as well. When a country upgrades its transport links to reduce internal road distance by just 10%, it can boost its total export volumes by 12%.